Hi, welcome to the first in the series, the new Electromagnetism application series. In this one, I keep getting a lot of subscribers sending me links to this YouTube channel called Theoria Apophasis. I hope I'm pronouncing that right. And there's one in particular experiment that he runs that's pretty interesting. A big thing is he claims that nobody can explain it, and I'm going to show you that new electromagnetism explains this thing hands down. And what has to do with breaking, not breaking something, but taking the energy out of something, breaking the motion of a wheel. Like when you brake your car, you're stepping on the brake pedal that breaks your motion. And this is electromagnetic braking. And the video, this is the link to the video. I'm going to put the video in the channel itself so that you'll be able to click on it to get there. He claims there's no models and theories that explain what he's demonstrating, and I'm going to show you that new electromagnetism explains what's going on handily. Okay, in the first half of this video, we're going to explain what was demonstrated. In the second half of the video, we'll dissect some of the arguments made in the video to educate the listener on how to properly identify what's valuable in scientific discussion and what isn't. So at approximately the 5-minute mark, he begins the demonstration after going through a lot of verbal discussion about things. And what he has is he has this humongous, I think it's somewhere between 6 and 8 inches in diameter. It looks like a neodymium magnet, not 100% sure. And he also has a little gyroscope. It looks like a brass wheel, a solid brass wheel, and it looks like it's inside an aluminum fixture to hold it. And what he does, he spins this up with something, I guess it's a Dremel or whatever. So this wheel is spinning at very, very high speed. And this is a very low friction bearings on this, so it spins pretty readily. And the first thing he does is he hangs this over the center of the magnet, where he claims that rest of science says is the majority of the magnetic field, the highest intensity of the magnetic field, and he holds it there and shows that nothing happened. In other words, the wheel spins freely, being only losing speed due to air friction or bearing friction or whatnot. Fine, no problem. And then in the next part of the demonstration, he puts the wheel near the edge of the magnet and shows that it breaks pretty readily. In other words, the wheel comes to a halt pretty fast. That's what we're going to call braking. Okay, so what I want you to do, if you already haven't seen the videos, is go through, and I'm going to put the links for the new magnetism part 1, part 2, and the new electromagnetism itself. You can do that now. If you've already been through them, or if you want to go do them later, that's fine. These are the models of new electromagnetism. Just as, and I'm going to call this guy TA for short, because I have difficulty pronouncing the Latin. TA, I agree with him that field model and classical theory is wrong. I've identified that over 20 years ago, and that's why I've come up with my own. The people that have followed my channel have followed it. Some people have been following me for 20 years. Okay, and if you don't know who I am, I'm an electrical engineer with over 30 years experience, and in that time I found that, yeah, we have problems with electromagnetic theory. It's not all, rainbows and lollipops. But some parts of it are good, some parts of it are bad. You take the good, throw away the bad, and improve the parts that are missing, and that's what I've done. And these are the 5 terms of new electromagnetism that I've come. Now, what I've done recently is, because I realize a lot of people have a problem with the vector equations, and they don't really understand it. To them, this looks like, hieroglyphics. I decided, well, I'll add more hieroglyphics. This is more of a pictorial model of what's going on. This isn't as complete as this, but it gives you a basic idea of what's going on, the forces. For example, this is Coulomb's model. It's not Coulomb's law, it's Coulomb's model, where it shows that 2 stationary like charges, if you have one and another, the force on the second is going to be radially away from the source charge. And for all of these, you've got to have one charge as the source, one as the target, and then you've got to do the opposite in reverse. So these equations only take the effect on a target charge due to a source charge, how one charge affects another across space. And that's one of the things I found. This is why I did this. It's because the Maxwell field equations are wrong. Their descriptions of magnetism give you contradictions, violation of conservation of energy. You can go to my foundation series and see all those derivations where I show you that they're wrong. The best we can do, what you can boil everything down in the universe to, is that every field phenomenon is generated by causing charges to behave a certain way. all field phenomena are measured by putting a field in, another charge in the field and seeing how it behaves. All you can do, and that's why I boiled everything down from a charge to charge effects. Get rid of the B field abstraction. The B field abstraction is not sophisticated enough to quantify all of the effects that you can observe in a laboratory. And that's what I've done. And I don't think we're complete with these yet. I think there's other effects that we've missed. And that's one of the things. I've got to get all these down before then we can go and theorize about what the fields are and whatnot. Okay, so we have Coulomb's model, and we have the magnetic models, and then this is new induction. And what we're going to do is we're going to mostly use the magnetic models for today. And the two of the most important ones are the second term of new electromagnetism, which basically says this is a charge in motion. The triangle means a charge in motion moving in this direction. This is another charge in motion, which would be the target. The source is on the left, the target's on the right. That if the target charge is moving toward the source charge, it's going to incur a force that's opposite the direction of the source charge. And likewise, if this charge were moving away, the sign of the arrow would be in the opposite direction. That's one of the ones we're going to use. The other one we're going to use is the fourth term of new electromagnetism, which basically says that like moving charges attract. Okay, obviously if they're going the opposite direction, they repel. Okay, and what the dotted lines mean is this direction is coupled to his direction, this direction is coupled to his direction. This direction is coupled to the center to center. It's just a radial force from the center of the charge. It has nothing to do with their direction. Same here. The force is not coupled to their direction. The force is just a radial distance between them. It's along the radial line of position between them. This symbol over here represents a charge accelerating, the double triangle. So in the new model of electromagnetism, I realized that, one thing I agree with TA is that the simple Gauss meter measurement of a magnetic field is not very useful. I agree 100% with that statement. And so in the new magnetism videos, I introduce this stuff you can get at Amazon. It's called MagnaView film. It's a few dollars. It doesn't cost $100 like the silly thing he wants you to buy. And in that we can see that this gives the best understanding of what's going on with magnets. That at the edges of the magnets is where the current, you can treat all magnets as a bunch of currents, and most of the time the current goes around the outside of the magnet. And I'm sorry, my MagnaView film is quite scratched up, so it's a little bit hard to see. Okay, I hope you can see that in the camera. So at the edges is where you get the majority of the current. And you can go through those videos I showed you, but you also have to be careful because some magnets, the currents actually zigzag through the body of the magnet. It's not necessarily along the edges. It depends how the magnets are made or how they're magnetized. And each one of those little black areas would be considered a domain in the terms of new electromagnetism. So that we can treat a disk magnet like the one he has as a big giant current ring, and the size of his magnet is probably in the area of maybe somewhere between 10 and 50,000 amps. And that's the model we're going to use. So let's first look at the example where he has the gyro, I'm going to call it, at the center. So what's going on? Well, let's first start with the second term of new electromagnetism, which says if this is moving toward this current, the current ring is out here on the outside. That's where the current ring of the big magnet is. And this is the spinning gyroscope here. So if you take the material, the gyroscope, which is in this motion in this direction, it's moving toward this current over here. And because it's moving toward this current over here, it's going to induce a voltage or a force that's going to be this way, opposite to the direction of this guy. And likewise, because this one's moving away from this one, he's going to develop a force that's like. Okay, if you're moving toward, you develop opposite. If you're moving away, you develop the same. He's going to develop a force that looks the same. Okay, then if we look at the fourth term, parallel moving things attract, we have the current, the charges, this metal disc is made up of equal amounts of positive and negative charge. Well, the charge that's moving parallel to the current in the ring is going to be pulled up toward. And so when you add these two arrows together, what you get is you get a voltage from the center of to the outside. So he's incorrect in saying nothing is happening. there is a charge buildup, that's charge moving to the outside of the ring. Okay, this is what happens in a homopolar generator. What he's missing here is a brush from the outside of the ring, which would pick up that charge and return it back to the center of the ring. In other words, if he put a little brush here and connected it to the metal frame so it would connect and return down the middle, then you'd get a current rotation through the wheel. That current rotation in the wheel will cause braking. Okay, so he's basically just has a homopolar generator. He almost has a homopolar generator. If we had the brush, he'd actually have the braking that would be caused by a homopolar generator. How does the braking work? Well, once you allow the current to move, instead of just charge building up, once you get current able to move to the outside, well, once you move to the outside, this current here now is now moving toward this guy over here. Once you're moving toward him, okay, if you're moving toward him, you're going to pick up opposite his velocity. That's going to cause a force in the opposite direction that the wheel is spinning, and there's where your braking is going to occur. Now, it would be much more efficient braking. Instead of having a solid wheel, he had a spoked wheel. That would cause much more efficient braking if he had, in fact, had a brush circuit. Instead of a solid wheel, a spoked wheel. That will brake much faster in this situation. Have much more braking force. Because instead of these charges that are moving to the outside just drifting through a resistive material, it would actually hit a non-area, it couldn't move and hit against something and actually apply much more force than just a simple braking action that you'd see with a regular homopolar generator. So, if you put it on the outside, well, same thing. If the wheel is moving this way, in this case here, this is moving opposite to this. And because these charges are moving in the opposite direction, that's going to affect a force through the center of the wheel here. Okay, there's not much that's going to happen in the other part of the wheel because it's kind of far away. The majority, the bulk of this stuff is going to happen in this region here, so that's where we're going to concentrate. Now, this material is starting to retrograde away from the current. If you start moving away from the current, you're just going to pick up the motion of the charge in the current ring. And that means you're going to pick up a flow of current this way. This material is moving toward the current. Because you're moving toward the current, you're going to pick up a motion in the opposite direction of the current, which is a motion of current in this direction. So what you're going to get is a rotation through the wheel of current that looks like this. So that's the current. Now, how does the braking occur? Well, because this current in the center is moving away from this current is going to pick up force in the direction, because he's moving away. He's going to pick up force in this direction. So it's going to have braking force in this direction. Because the current, unlike this case, where the charge is all moving to the outside and has nowhere else to go, this current has a place to go. You're pulling it in, and you're pushing it out. And so it's going to circulate in the disk in this fashion. And so because it is circulating, you're going to get braking. And that's why he gets braking on the outside. Again, as this current is going through the center, because just like the second rule says, if you're going toward, you pick up the opposite. If you're going away, you pick up the same motion. Since this current is going away, it's going to pick up the same motion, then you're going to get force acting on the disk in this direction. Over here, because this current is coming in, it's in parallel. Now we're going to the fourth. This current is in parallel, but in the opposite direction. So there's going to be a backward force this way on the disk, and because this is coming in parallel but in the same direction, there's going to be a traction in this direction. So you're going to get force, a little tiny bit of force in this direction, a little bit of tiny force in this direction. That's why you get the braking on the edge. Now, if I could quantify, if I can get a real measurement how much current is in this magnet, if I could find out what the mass and the dimensions and the material are in this disk, and how fast, what he's using to get it up to speed so I know how fast it was turning, I could probably tell you exactly where you could put it to get even more braking. I think that's probably halfway down the side. I'm not 100% sure, because sometimes these things, you really have to go through the math to find out where the optimal points are. But he's pretty close to the optimal point in this direction. Now, the other thing is, if this were a spoked wheel, it would brake a lot faster. Again, if it were a spoked wheel, it would brake a lot faster because the current would actually be hitting up against an air conductor boundary as opposed to just drifting through conductor. So this would break faster if it was spoked. And he doesn't need to put a closing path because the closing path, or the closing path is actually through the wheel itself. And that's why, because it's going through the wheel, it's not as efficient. If he had, in this case, if his wheel were almost the same size as his magnet, okay, the braking force on this case, if he had the closing path, would be a lot more powerful than the braking force of having that same wheel being run off the edge like he does in this case. Okay, so this is easily explained. Now, to be fair, classical theory doesn't properly explain the homopolar paradox, or the homopolar theory. Its new electromagnetism explains it real easy. We can do a lot of quantifiable stuff if I had some quantifiable measurements. This is just to blow up what I was going to do. Okay, so classical theory does not explain homopolar effects very well. New electromagnetism does. This explanation is one of the many free papers that I've published for over a decade at my site. If you go to distinti.com, docs, this is, you can browsable. Now, a lot of these documents are getting old and outdated, and back in the old days, I was a lot like him. I used to put everybody else down that didn't agree with me, and I used to think stuff was irrefutable. I've gotten older and more mature over the years and realized that, the best we can do in science right now is to find theories that agree with what we observe so we can build fantastic machines and take humanity to the next level where we'll find the new contradictions to what we think is the truth. Okay, that's the best we can hope for. So it doesn't really matter what the truth is can we do things in a repeatable way where we can develop machines from them. Now let me do a little critiquing of TA. Now, I agree with about 50% of his statements. However, in many cases, he actually violates his own decrees. Like in 2 minutes and 5 seconds in, he claims there's no explanation at all. Well, of course, I disagree with that. But he himself offers no quantitative explanation either, at least that I could discern. He's got a lot of interesting subjective explanations, like, he goes a centripetal thing, like stuff going down the drain. But those descriptions are fine, but without a quantifiable one where you could actually use them to optimize the design of a machine, they're of really no value. And because he makes a demonstration really without really offering any theory, he states the descriptions are not explanation, and that's true. That's absolutely true. But demonstrations are not explanations either, and all this really is a demonstration. He offers really no explanation other than, like I said, the subjective explanation, which is really of no value without quantifiable a mathematical equation that you could use then to develop an optimal braking machine or an optimal machine or an optimal something. At 1 minute and 30 seconds, he has said a field has no quantity. Well, I'm sorry. If anything affects something else, can be quantified. Okay, if I have this magnet over here, and I'm able to put another magnet in its field and feel the force and feel the torque and whatever, well, then I can quantify this magnet. Okay, so sorry, everything has quantity. Now, maybe what he was trying to say, okay, is that a field has no particles. I don't know. It doesn't really matter. Right now, I'm going to tell you the absolute truth. Nobody really knows what a field is. Nobody. Not me, not him, not any scientist. All we know is a field is something where a charge affects another charge across the distance of space. That you can model it with a system of particles is not a problem as long as you get correct answers. Because it may be 1,000 years from now where we're finally developed something that we can go and actually look and see what a field is. But until then, all we have are models that mimic the effect and the behavior so we can develop machines. That's all we can hope to have. Anybody that claims other than that, oh, we know what something is retarded. I'm sorry, that's the right word. And models do not have to be true to be useful. Okay, like I said, if you want to model a field as unicorn urine or this kind of particle or hay fever particles, it doesn't really matter. As long as you can get repeatable, useful answers where you can develop machines that will carry us to the next star, it really doesn't matter what abstraction you use. It's really all of it. Mathematics is an abstraction anyway. And he also says these fields are not quantifiable, but at 2 minutes and 5 seconds, He goes and points at the center of the magnet and to the edge of the magnet, says there's only a 5% difference. I'm sorry, if you're saying there's a 5% difference, and you've obviously quantified it. So you can't say there's no quantity if you're quantifying it. Finally, I agree with this notion that Gauss meters by themselves are quite clumsy, but engineers have known that, and we know how to use them to be able to make useful measurements of magnets. So he's not stating anything that we don't already know. And he's wrong at 714 where he says Gauss meters measure flux over time. No, Gauss meters measure flux instantaneously. There's no temporal thing there. Unless you decide to put it on a chart recorder and measure flux over time, the Gauss meter by itself does not do that. And 716 says all Maxwellian equations have a temporal variable. That's wrong too. There are static fields, static equations. So, you know, if you're going to say everybody... Now, I agree that Maxwell's equations are garbage. But at least if you're going to critique Maxwell's equations, at least know what you're critiquing and understand them. Because the only way you can critique them is to really understand what they are, to be able to say, hey, this does not match this. That's what I do in my videos. I show you where Maxwell's equations disagree with theory, or where engineers don't even use the theory. They use something else. Okay, that's in the Foundation series where I basically tear James Clerk Maxwell a new asshole. Well, I'll be producing a magnetic field measuring device using a standard flux meter and coupled with software that allow you to take measurements so you'll be able to quantify a magnet in terms of current like I do. This will be a much better, easy to use model of a magnet than the Gauss model. And I agree with him, the Gauss model is not the best model. My problem is that I'm working 60 to 70 hours a week. I've got heightened responsibilities at work. I've been losing time on putting time toward ethereal mechanics. I apologize, and hopefully this will abate pretty soon, and I'll be able to get back to a more productive schedule. So I apologize to my followership for producing very little over the last couple of months, but I've got heightened responsibilities at work. Anyway, thank you very much.